Well, thank you everybody for coming. It's a great pleasure to be the first of the head people to talk to you today. By head, I mean the opposite of heart, rather than in charge of everything. And in particular, I'm going to be telling you a little bit about the world of quantum mechanics and the world of particle physics. And by the end of this 12 minutes, you should have an idea what this picture is and why I spent several of my formative years down a mine in America. And so, before we start talking about the world of quantum mechanics and particle physics, it's worthwhile just to have a little moment to set the scale of the sizes that we're going to be talking about in our quantum world. So this is a little chart that I borrowed from a friend of mine, Michael de Podesta, where in the middle, that little blue person in the middle, is our average everyday person. Everyone in this room is just around the meter scale. We're all kind of 1 meter plus or minus a meter, thereabouts. And everything we deal with in our day-to-day life is measured in meters, like the size of the train, the size of the house, etc., etc. And we can start thinking about those things that are much bigger than us. And we can think about what's the largest thing on the planet. And maybe you think of Mount Everest. And there you're looking at scales of thousands of meters. Or you can think of the size of the planet itself. And there we're looking at scales of millions of meters. Or we can look at, what's the nearest thing outside our planet? We can think of the distance to the sun. And now we're looking at trillions of meters. And we can think, what's the nearest thing outside our solar system? And we can think of, the distance light travels in a year, or the distance to our nearest star, which is, 1 followed by 16 or 17 zero meters in size. And we can go all the way up to thinking about what's the largest thing that we know about, which is the universe. And we think our current estimate of the size of the universe is 1 followed by 29 zero meters in diameter. Right? This is an unimaginably large number. And those big sizes have quite a lot to play in the quantum world. But most of the time we're looking at things that are smaller than ourselves. So we can think of things that are maybe, the diameter of one of our hairs, which is 50 millionths of a meter or so. Or we can think down to microbes or to the chips that run our computers and our smartphones. And now we're talking about structures that are built on the size of a billionth of a meter. And then we can go all the way down, and most of us remember from school that everything is made of atoms and molecules, and each of those atoms is made of a positively charged nucleus in the middle and a cloud of negative electrons around it. And then if we look inside that positively charged nucleus, we can break things down smaller and smaller until we get down to our fundamental constituents of matter, which are our quarks and electrons, which are the smallest thing we've ever managed to measure. And when we get down to these tiny, tiny sizes, the world of quantum mechanics starts to become important. And I'm giving a talk on quantum mechanics, and so I should probably make a slight confession here. I don't really believe in quantum mechanics. I mean, it is very useful. It does predict all of the data we've ever managed to measure anywhere else. But it just doesn't, it doesn't somehow seem believable to me, because there's one simple rule of quantum mechanics, and if you understand this simple rule, you understand everything there is to know about quantum mechanics. And that simple rule is anything that can happen does happen. And that's all there is to quantum mechanics. And that's why you get these little thought games where scientists are torturing cats, and the cats are either dead or alive, because until you open up your box and have a look inside, both possibilities can happen, so both possibilities have happened. And it's only when you actually look that you find that one of those possibilities is made real. And there are various other things that quantum mechanics tells us. It tells us if we think about light, there are little particles of light, little bundles of light. We call them photons, and at certain energies, those photons behave as though they're waves. So our television antennas that used to sit on top of our houses, or our satellite dishes that sit on top of our houses, are all detecting electromagnetic waves, which are these photons making little wave shapes. But then at higher energies, we get pictures like the one in the top right-hand corner there, which is actually a particle physics experiment in Japan, where each of those little balls are detecting these photons as particles. And this duality, this fact that photons are both waves and particles at the same time, is something that is coming directly from quantum mechanics, and it's something that we can't really explain. But we know that in order to explain the universe we live in, we have to come up with these dichotomies, that everything is happening simultaneously, and things are behaving both as though they're a wave in the sea and a pebble on the beach. So you'll hear a little bit more about recent breakthroughs in particle physics a little later on this evening. But here on this one slide are all of the particles we know about in the universe. There are 12 particles that make up the universe, although we only actually need 3 of them to make up everything that you've ever seen, tasted, touched, smelt, etc. So that we have these up and down quarks, which are used to make the different nuclei of the different chemical elements, and the electrons. And those 3 particles, the up quark, the down quark, and the electron, that's all you need to make yourself, this building, all the rest of London. And then in this first column here, we have this extra particle. It's called a neutrino, and I've spent most of my adult life trying to understand the properties of neutrinos and see why we have this extra interloper in this first column. Other things we don't understand about particle physics are why there's these 2 other columns there, which are just the same as the first one, only seemingly heavier. And we just don't understand why that is. Now, if all we had was just these particles, the universe would be a very dull place. So we'd have all these particles, and there'd be no way for them to talk to each other. There'd be no way for them to interact. So there are 4 forces that we know exist. There's something we call the strong force, which is the force responsible for holding the quarks together to form the nuclei in our body. There's electromagnetism, which, in addition to giving us the delights of cell phone and light, is the reason that we have all of chemistry and most of biology, and that's the reason that atoms and molecules can stick together. Then we have gravity, which is the reason that planets and stars can stick together. And then we have one last force called the weak force, and all it does is provide a mechanism for the sun to make energy. And it also gives us some radioactivity and things like that. And neutrinos are kind of interesting because they're the only neutral particle that's in these 12 particles of matter, and they only interact through this thing called the weak force, which means that it's kind of tricky to detect. And I'm giving a talk about neutrinos. I'm somewhat contractually obliged to include a photo of this gentleman, Wolfgang Pauli, because in 1930 he's the gentleman who invented the neutrino. People had been measuring radioactive decays, and they observed that they didn't seem to conserve energy. And conservation of energy is something that, if you ask any physicist, that we believe you should probably do. It's one of those nice laws that helps the universe keep existing. And so, in order to keep conservation of energy, Pauli said what must be happening is some hidden, invisible particle is stealing away some of this energy. And when he did this, he said, today I've done a terrible thing because I've invented a particle that can never be detected. And it's not quite true to say that it can never be detected, but it did take a good 30 years after he invented it before someone managed to detect one of these particles. My favourite thing about Pauli is that his wife left him. That's not my favourite thing. But when his wife left him, he said, had she taken a bullfighter, I would have understood. I could accept that as a man, but to leave me for an ordinary chemist. It's good to know that even back in the 30s and 40s, physicists had a healthy disdain for chemists. So I mentioned this weak interaction, which is the only interaction that the neutrino feels. And so why do we call it the weak interaction? Well, unsurprisingly, we call it the weak interaction because it's very weak. And to give you an idea of how weak it is, the sun burns through a process of nuclear fusion. And when this happens, there are 2 particles that are produced. There's something called the positron, which is the anti-version of the electron, and that will travel for about this distance, so about 3 centimeters of water before it interacts. And the neutrino that's produced in the same process will travel through 53 light years of matter before it interacts. So the difference between the weak force and the electromagnetic force is 3 centimeters to 53 light years. So that tells you if you want to build a neutrino detector, you're going to need a lot of neutrinos, and you're going to need an awful lot of detector. And the first kind of people who put these together were doing things like this, where they were going down to a mine, creating these enormous tanks, not so that they could just go swimming in them, although he seems to be doing that. Basically, that enormous tank got filled with bleach. He's not swimming in the bleach there, he's swimming in the cooling water pool outside the bleach. And then down in the bottom, there's someone else going swimming through one of these neutrino detectors, where you build this enormous tank of water or some other material and hope that one of these neutrinos may occasionally strike something in your detector. And that, that's all very well and good, but nowadays we have slightly more sophisticated means. And so one of the experiments that I've been working on for the last decade is called the Minos experiment, and it uses a bit more of a brute force approach. We, rather than relying on neutrinos from the sun or one of these other natural sources, we create our own beam of neutrinos at a particle accelerator lab in America called Fermilab. And over the last 7 years or so, we fired a sextillion neutrinos. So that's 1 followed by 21 0 neutrinos through the Earth, and they just fly merrily through the Earth. And then a tiny fraction of them, so of that sextillion neutrinos, maybe a few thousand of them have hit this 5,000-ton detector that we've stuck at the bottom of the mine in Minnesota. And you may ask, why are we firing a sextillion particles through the Earth to catch 1,000 of them at the other end? And it's a good question. And we're going to illustrate it through the medium of ice cream. And so we know that neutrinos come in these 3 flavors. We call them electron flavor, which we're going to represent by chocolate, muon flavor, which we'll represent by vanilla, and tau flavor, which we'll represent by strawberry. And in Fermilab, which is just near Chicago, we create a beam of vanilla ice cream. We fire it through the Earth, and at this mine on the other side, we have a mixture of flavors. And by looking at how that mixing happens, we can say something about the properties of the neutrino. And the reason that we're interested in doing this is that we're trying to answer some fundamental questions about how the universe came to exist. So we know that all of the universe we see is filled with matter, but we know that whenever we create the Big Bang conditions at places like the Large Hadron Collider, we create matter and antimatter in equal parts. And so one of the biggest questions out there in the particle physics world is, where did all the antimatter go? And it may be that neutrinos have something to do with that. It may not be. In addition to firing sextillion particles through the Earth, I also spend some of my time flying balloons in Antarctica looking for high energy particles coming from the other side of the universe. And so this is just like a little slideshow. This is what I do on my holidays, kind of thing. And so, earlier on, I said that quantum mechanics tells you that anything that can happen does happen, and obviously, Murphy's law also tells you that. And so we built this 5,000-ton detector, half a mile underground, and the way you get down there is in a lift shaft that's lined with these timber beams. And a couple of years ago, the timber beams caught fire. And so you can ask yourself the question, how do you go about putting out fire if it's half a mile underground and there's no way of you getting down there because it's too hot, there's too much smoke? And the answer is you just pour millions and millions of gallons of flame retardant foam down there. And so a couple of years ago, my detector that I'd spent 10 years working on looked like this. It looked like it was having a bubble bath in this fire retardant foam. Unfortunately, it's not a story of woe and distress, because we managed to clean it up and get it working again. And so one of the things we learn about quantum mechanics is it gives us features like these neutrinos changing flavor as they move throughout the Earth from Chicago to northern Minnesota. And it can also be used potentially in the future for things such as quantum computing and quantum information. And that all relies on the idea of quantum entanglement and quantum interaction, where 2 particles can come together, interact with each other, and be caught in some little world until some other particle comes in and changes how we interpret that. And now you're going to see that through the medium of artistic representation.